Oh, silence. All right, class 13 here, 4 in Zoom, 17 out of 50 students. Yeah, well, we know who's gonna pass, right? I mean, if you're already a master of calculus, right, just CLEP out of the class. Y'all familiar with CLEP? CLEPP, right? You could go take an exam and test out of college classes, like $100 or something. And you don't have to be enrolled in college at all. But if you pass the test, that credit will transfer to any college in the country. Some are easier to pass, like intro to literature has like a 90% pass rate. I mean, you just like watch some movies on Shakespeare or whatever, and then go take the test, you know. Some CLEP tests have a lower passing rate, like chemistry 2, you know, it's like a 10% pass rate, you know, but it's worth it to at least try, you know, save yourself 4 months of studying, and I don't know how much tuition is these days. Yeah, check out CLEP tests, you know, for those core curriculum classes that, you know, suck. You know, some of them you could probably, you know, take a summer off and just do a little bit of study and save a bunch of money. But just do some research, like look at that CLEP test and see what the passing rate is, so you know which ones the easy ones are, you know. I took the chemistry 2 one after like auditing chemistry 2 twice. Sat through the class, did all the homework, tutored the whole time, and I still couldn't pass the CLEP exam. It was just hard. It's the only class I needed to get a 3rd bachelor's degree in physics. But oh well. So let's see. First derivative test. So last time we learned that when you take the derivative, where, look at a picture of this, where the slope is 0, or where the derivative is 0, that's where a local minimum or local maximum can occur. So like here, you can see right there at that point, the slope is 0, or the derivative is 0. So if the derivative goes from being positive to negative, right? To go from positive to negative, you have to cross through 0, right? So that would be a local maximum. A local minimum, you can see the first derivative goes from negative to 0 to positive. So that gives you a local minimum, okay? See here you have negative to positive. I don't think the slope here exists though. This is one of those jagged points, right? So here the slope is undefined. But either way, it's a critical point. Remember, the critical points are where the slope is 0 or undefined, okay? Here is an example where it's increasing, 0, and then increasing, right? So that's not a local minimum or maximum, but it is a critical point. So a critical point doesn't mean local min or local max. Local maximum or local min does mean a critical point though. See what I mean? All right, so you can have a critical point that's not a local min. This is called an inflection point, right? These are inflection points, basically. And here's another one where it's negative, 0, negative, or negative, undefined, and negative. Remember, if you have a line that's straight up and down, the slope there is undefined, right? Is this line going straight up or is it going straight down? Is the slope positive infinity or is it negative infinity? Or it's both, right? This is a slope of 0. A vertical line is an undefined slope, okay? So like the difference between these two is really hard to tell. Right here, the slope becomes 0. Right here, they're saying there's this tiny little straight line right here. There's a tiny little portion of it that's vertical. See, right here, it's just 0, right? Right here, it's straight up and down. Straight up and down is undefined. So this is a critical point where the first derivative is undefined. This is a critical point where the first derivative is 0. Either way, they're critical points, but in neither of these scenarios is it a local extrema. So the first derivative test just basically gives you your critical points, and then you need to look at those critical points and test to see whether they are minimums or maximums. Does that make sense? Okay, so let's look at a problem here. Let's see. Use the first derivative test to find the local extrema of f of x. Okay, well, first derivative test. Let's find the first derivative. 3 times 2 is 6. 2 times 3 is 6. And we have minus 72. So there's our first derivative. It's a nice little quadratic, right? If we set this equal to 0 and solve, right, this is a piece of cake, quadratic formula. Or if, I mean, in business, you're really never going to get like these numbers. You're going to have some horrible decimals, right? In reality, most things have horrible decimals. So you're almost always going to use the quadratic formula in reality, okay? But in here, they want us to use our basic algebra. If I divide everything by 6, I'll write it like this. The prime of x divided by 6 would be x squared minus x minus 12. Okay, so to factor this, we should be able to eyeball factor this, right? Because there's no coefficient here. I need an x and an x. And I want a 3 minus 4 plus 3, right? Minus 4x plus 3x gives me that minus x. Right? I got the minus 12 and the x squared. So there we go. So either x is 4 or minus 3. Those are the critical points, right? So usually you want to kind of draw your little line here and be like, okay, over here, 4, over here, minus 3, those are our critical points. So we just want to test and see whether the first derivative is, I mean, this is where it's 0. That's where the first derivative is 0. So we want to see, is it positive or negative in these intervals? So we just pick like a test point, right? So let's look at f prime of minus 4. We just pick a point over here to see if it's positive or negative. And rather than plugging it into this, right, I just want to know if this is positive or negative. I'm going to plug it into this one, right? Because if this is positive, if this is positive, so is this, right? And it's just easier to plug it into this, because why multiply everything by 6, right? So this would be minus 4 squared minus a negative 4 minus 12. So this is what, 16 plus 4 minus 12, which is positive, right? So that means that f prime is positive over here. Does that make sense? I hope I'm not making things difficult by plugging it into this one instead of that one, right? This is positive when this is positive, right? The arithmetic's just easier here. So we know it's positive there. Let's pick a test point here in the middle. Let's pick out 0. We'd have 0 squared minus 0 minus 12, which is negative. And now let's pick a test point over here, like 5, right? We would have 5 squared minus 5 minus 12. This is what, 25 minus 17, which is positive. Okay, so if you think about it, right, these are our critical points. It's going to be increasing, then it's going to be 0, and then it's going to be decreasing, right? And then it's going to be 0, decreasing, and then 0, and then increasing. We have something roughly looks like that. So you can see that at minus 3, that's going to be a local max. And over here at 4, right? Where it's decreasing, 0, and then increasing. This is going to be a local minimum. That make sense? This is our first derivative test. Pretty easy stuff, right? Take the derivative, find the zeros, and then figure out where it's positive or it's negative. Maybe that solution here will give us a nice little. Here's a little chart. A little picture. -4, 0, and 5, and they picked. Yeah, I'm sorry. -3 and 4 were our critical points, and they picked the same test points I did. So. Oh, before I forget, the guided notes, the weekly uploads on Monday, I forgot to release them. I released them today. So for 12.1 and 12.2, your guided notes and your written homework are now available for you to do. You're going to do by Monday, just like every week. Okay? So don't forget about those. Here. All right, let's do another one. First derivative test. Okay, well, here's the function. Let's find our first derivative. Let's see, multiply the exponent. 4/3 times 3 would just be 4. Then we subtract 1 from the exponent. And then 12 times 1/3 would be 4. And then we subtract 1 from the exponent. Okay. So now we want to set this thing equal to 0 and solve, right? Because that's going to give us critical points. But remember, there's also the critical points where the derivative is undefined, right? And so you can see right here, you can't divide by 0. So x equals 0 is a critical point. Okay, that makes sense. This is really, you're dividing by the cube root of x squared, right? This guy, just for a note here, x to the -2/3. This is 1 over the cube root of x squared. That makes sense? Okay, because remember, like x to the 1/3 power, that's the cube root of x, and an exponent to an exponent, you multiply. Okay, so that's the way you would want to think about that. Yeah, let me put this over here. Nope. I mean, this is algebra stuff, but that's the kind of stuff that gets like easily forgotten or not absorbed, right? Until it shows up constantly. Okay, so if we're going to solve this guy, first thing I'm going to do is divide everything by 4. All right, so I got x to the 1/3 minus x to the -2/3 equals 0. So if I want to solve this guy, I'm going to multiply both sides by x to the 2/3 power. All right, I'll go ahead and write it out. All right. So x to the 2/3 times x to the 1/3, we add the exponents, that's x to the first power. X to the 2/3 times x to the -2/3 would be x to the 0, and anything to the 0 power is just 1. See how quickly that cleaned up? It went from some crazy exponents to this. Therefore, x equals 1. Hopefully I didn't do anything that lost a solution there. Y'all follow this step? Questions about that? Come on, I know some of y'all have questions about that. Okay. All right, so the critical points are at 0 and at 1. So let's go down here. We'll be like, okay, 0 and 1. I'm gonna steal this guy. So we need to test our intervals here. All right, so again, wherever this is positive, so is this, because all I did was divide by a positive 4. So the arithmetic is easier here. So I'm gonna pick like a -1. -1, 1/3 power, minus a -1 and -2/3. Okay, what is this? This is gonna be fun here, right? What is the cube root of -1? Anybody tell me that? Remember, cube roots are, you can't take the square root of a negative number, right? If I took the square root of -1, this is I. Or if I took the 4th root of -1, this is minus I. Anyhow, it's a complex number, okay? But the odd roots are just fine. This is just -1. Why? Because -1 times -1 times -1 is -1, right? That's straight up definition of a cube root, right? Now let's look at this guy. Let's look over here. Let's see, -1 to the 2/3. That would be this guy squared cube rooted in 1/, right? Right, because it's to the negative power. That means we're dividing an exponent to an exponent. So let's look at this. This would be the cube root. What's -1 squared? 1, right? What's the cube root of 1? Well, it's just 1, right? Does that make sense? How we work through that? It wasn't as difficult as it looked, right? Okay, so we have -1 minus 1, which is -2, right? So that's negative. So over here, the first derivative is negative. Okay? Now let's pick something in here. What, like a half maybe? We'll do f prime of a half. So this would be 1/2 cube rooted minus 1/2 to the -2/3. Okay, so this is just 1 over the cube root of 2, whatever that is. It's some positive number, right? And then this guy, what is this? Let's see what it is. This, because it's a negative exponent, remember the negative exponent tells you to divide. Well, we're already dividing, so that's going to turn that to a positive exponent, right? This would be 1 over 1 over a half to the 2/3, and that's just 2. So follow that step. Got rid of the negative exponent and flip this guy over, okay? Let's see. What is this? This is the cube root of 2 squared. Yeah. Or the cube root of 4. So this is the cube root of 4. So this is something we might want to type into our calculator. It's hard to tell if that's positive or negative by looking at it, right? Let's see, we could do this, right? To see which one's bigger, right? If we're comparing these. Bigger or negative, right? We could try something like that. If we cube both sides, right? If we cube both sides, we would have 1/2, is it bigger than or less than 4? See that comparison there? Okay. And if this is bigger, then this thing is positive, right? If this one's bigger, then this thing is negative. Well, 4 is bigger than a half, so this is bigger than that. So I would make this thing negative. Does that make sense? All right, okay. So that means it's negative in here. So, which it's kind of interesting, it's decreasing, and then we had a critical point, and then it's decreasing, right? So I think this is an example. Remember, this was where we plugged in this because that's where the first derivative is undefined, right? So I think that's one where you're getting, it's going like straight down, right? It's where the slope is undefined, okay? This is where the derivative was just 0. So let's look at the test point over here. So we'll plug in like 2. So f prime of 2 divided by 4b 2 to 1/3 minus 2 and negative 2/3. This is what the cube root of 2 minus 1 over the cube root of 2 squared. All right. This is the cube root of 2 minus 1 over the cube root of 4. Okay, how am I going to do this without a calculator here? Okay, so which one of these is bigger? This one, less than or bigger than this? Well, if we cube both sides, okay, which is bigger, 2 or a 4? The 2 is bigger. That means that this number is bigger. So if you have a number bigger than something you're subtracting, that would make this positive, right? Or you can type it in your calculator, right? Okay. So we have something that looks like this. It's decreasing, then it's undefined, and then it's decreasing, and then it's 0. The first derivative is 0, and then it's increasing. So that's kind of the shape of things that we have over here. Okay. So this is going to be not a local min or a max, right? I'll put NA for not available. And then right here, this would be a minimum, right? Because it's decreasing and then 0 and then increasing, okay? Let's see what kind of tricks they invoke in their solution here. I mean, I did it my way, but there's lots of different ways of thinking about this. So we had the first derivative. They did the same test points I did. Again, I did everything divided by 4. So all they have is everything is multiplied by 4 on top instead, but that doesn't affect whether it's positive or negative. They wrote it as cube root of minus 1 squared, so it'll be the cube root of 1. Okay, and then this one, they got the cube root of 1/2 squared down there. So they got negative, negative, positive. It's the same thing I got, negative, negative, positive. Okay, so I didn't screw it up. But I mean, these kinds of things, I just wanted to kind of go through those in a little bit more detail. You probably haven't seen those a whole lot. You haven't had a whole lot of practice dealing with weirdo fractional exponents, okay? There's no local extremum at x equals 0, and there is a local minimum at 1 by part 2 of the first derivative test, okay? Oh, any questions on this one? Okay. This is fun stuff, huh? Wait until we get to the second derivative test. I mean, if you understand slope, it starts to become common sense, you know, it's not really that technical here. Use the first derivative test to blah, blah, blah. Do the same thing we just did twice in a row. Okay, well, this one is a rational. It's a polynomial over a polynomial, right? So what is our first derivative? Let's see. We can do what, the quotient rule? Or we could do the power rule, right? This is really x times x squared plus 1 to the minus 1. You want to do the product rule? I mean, the power rule with the product rule or quotient rule? Don't care. You could do it either way. We'll do the quotient rule. Let's do that. Why not? We get the bottom thing squared and then the bottom thing. times the derivative of the top thing minus the top times the derivative of the bottom. So this is x squared plus 1 minus 2x squared. And we can simplify that more. X squared minus 2x squared, the minus x squared. So we got a 1 minus x squared over x squared plus 1 squared. Y'all might want to write these backwards. I just don't like having the minus sign out front. I'd rather look at 1 minus x squared than negative x squared plus 1. All right, it's fewer pen strokes to write it this way. All right, you don't have to write a plus and a minus. This way you're only writing a minus. All right, I was aiming for the fewest number of pen strokes to represent something, right? Okay, so that is our derivative. Let's see. I mean, we could factor that, right? Probably just have to factor. I don't think we can reduce this. This is a sum of squares squared, so we can't factor the bottom, right? So where's this dude? 0 or undefined? You might think, well, you can't divide by 0, but no matter what number you plug in, positive or negative here, when it gets squared, you got a positive number, right? Even if you plug in 0, if I plug in a minus 1, squared is still positive 1, and then I add 1. So the bottom is never 0. This is never 0. So you'd have to plug in an imaginary number to get 0 on the bottom of that thing. Okay, so we don't have to worry about that. This thing is 0 basically only if the top is 0. Okay, and then we'd have, well, okay, x squared would have to be 1. So that means x would have to be a positive or a negative 1. So those are our critical points. So we'll do our little thing here. Minus 1 plus 1. Here's our f prime. I want to forget about that. So let's pick a test point. I'll pick out negative 2 here. So that 1 minus negative 2 squared over negative 2 squared plus 1 squared. This is 1 minus 4. And then this would be a 4 plus 1. 4 plus 1 is what, 5 squared? So this is negative. 1 minus 4 is negative. So let's look at a test point in here. 0, right? Let's see, I would have 1 minus 0 squared over 0 squared plus 1 squared. So this is 1 over 1, which is 1, which is positive. And now we'll pick out a number over here. We'll pick out 2, right? F prime of 2 would be a 1 minus 2 squared over 2 squared plus 1 squared. This is 1 minus 4 over 25, which is negative. If you think about it, right, we're going decreasing, 0, increasing. So we're going decreasing, 0, increasing, 0, decreasing. So you can see, right, this is at our minus 1, this is at our plus 1. So this guy here is a local minimum. This guy here is a local maximum. Question? All right. Minus 1 plus 1. They check them. Blah blah blah. Here's the picture. I'm gonna put their little diagram in here too. Their little picture's better than mine. Right? Minus 1, 1, decreasing, increasing, decreasing. Oh, this is what you really want to do. Graph, right? Every single problem you get, use Desmos or your calculator or whatever. At the very beginning of the problem, you see something like this. I don't know what that looks like. right? I know what x squared looks like. You know, there's a lot of toolkit functions. I will roughly know what it looks like. I know a quadratic is a parabola that's been shifted. I don't know what that looks like. So the first thing you want to do is graph, so that you start getting, if you do that with every problem you have, eventually you'll get an intuition, you know? Don't just graph it and be like, there it is. But graph it and spend a couple of minutes thinking about, why does this graph look like that? So you can build that intuition. So later on, when you start seeing random functions, you might be like, oh, I kind of know what that looks like, you know? So start practicing that there. I mean, x, the graph of that is that. This is x squared shifted up one, right? That's this. So somehow that divided by that gives you this. Right? Right? If you take all the y values here and divide by the y values there, you get the y values here. Right? But you can see at 1 is a max and at -1 is a min, and the slope is 0 there. Right? You can see it's decreasing, increasing, 0, and then decreasing again. Okay. I want to work the checkpoints too, but I'm afraid we won't have time. There we go. This one just has an e to the x in it, right? Find local extrema. Okay, first derivative test, right? So our first derivative, we'll do the product rule, right? Let's say, I want to do this. I'll do first function times the derivative of the second. The derivative of the e to the stuff is e to the stuff times the derivative of the stuff. Now we have the derivative of the first function times the second function. All right, and we can simplify this, right? We have a 5x squared plus a 2x, and everything is e to the 5x. And really, these both have x's in them, right? So maybe I'll pull an x out as well. I factored as much as I can ahead of time. You might want to write the x out front here. I'm going to put it out front. Looks better over there. So where is this guy equal to 0? Okay, well, we have 3 factors here, right? This guy is never 0, right? Exponentials always look like this. They go through 1 and then they blow up, right? They get closer and closer to 0, but this is always positive. So that's 0 if and only if this part is 0. Again, because that guy's always positive. Right? So that's 0 and only if either x is 0, right? Or this is 0, and that's 0 when x is what, a -2/5, right? Set that equal to 0. Remember that? Right? Factor, set each factor equal to 0. Okay. So those are our critical points. Now we want to do our little test here. So we have 0, 0, and -2/5. So let's check a point. Over here, something simple would be like -1. So here's f prime. So we would have a -1 times a 5 times -1 plus 2 and e 5 times -1. Again, this guy's always positive. So really, we don't even need to deal with that, right? I'm going to throw it in there just for fun. So we have a minus 2 minus 5 is a -3, right? And then whatever, e to the -5. This guy's always positive. A negative gives us a positive number. Right? This guy is always positive. E to the anything is a positive number, right? Just because that's negative, don't make that anything. That's 1 over e to the 5th. This is 2 point something to the 5th power, right? That's a positive number. All right, let's pick something in here. Maybe like negative 1/5. Negative 1/5. 5 and the negative 1/5 plus 2. And then e to the 5 times negative 1/5 is 1, right? Doesn't matter, this is positive. 1 over e is positive. So we have a negative 1/5. 5 times a minus 1/5 is a minus 1. Right, this is positive. 2 minus 1 is 1 times a minus 1/5 would be a negative number. So this is negative in here. Okay. And now let's pick something over here. Let's just pick 1. Why do I have the same thing here? This is minus 1/5. Sorry about that. We're plugging in a minus 1/5. That's the same thing twice. Y'all got to point these things out. Come on now. Y'all like my hive mind, checking my every step, right? Collective consciousness. Right? Now we're going to plug in a 1, because that's over here. So we would have 1 times 5 times 1 plus 2 times e to the 5 times 1. And these are all positive numbers, so this is definitely positive. So you can see we have something increasing, and then it's 0, and then it's decreasing, and then it's 0, and then it's increasing. So this is going to be max. This one's going to be a minimum. All right. So here's our graph. This will give us a pretty graph. That's x squared e to the 5x, right? If you think about it, this is an exponential. Exponentials blow up real quick, right? X squared is a parabola. It increases, right? But exponential goes up a lot faster. So this guy, as a graph, is dominated by this exponential, okay? You want to think about things, rates of increase, right? Parabola, you know, an x squared is going to be like this, right? Whereas an exponential does that, right? Especially as the numbers get bigger and bigger, right? So like right in here, real close to 0, they're kind of close to one another, right? X squared, right? If you plug in a 2, right? 2 squared versus, again, e is 2.7, right? Squared, I mean, those are kind of close, but once you get to like 10 versus 2.7 to the 10th power, this is huge compared to 100, isn't it? So just by the time you get over here to 10, this guy is off the screen, right? So the graph of this thing is dominated by the exponential portion, okay? That's where Priceline cost. The cost function in millions of dollars for Priceline Group Inc. can be approximated by C of X here. For X corresponds to the year 2000 by X equals 0. Determine when costs are increasing and when the costs are decreasing. Also find all the local extrema. So first derivative test, right? Okay, so first off, we need to find the derivative. If I multiply by the exponent, I'm going to get a -7. Subtract 1 from the exponent. 2 times 53 would be 106. And we have -295. So that's the derivative of cost. So we need to find our critical points. Let's see. Maybe is 106 divisible by 7? No. uh, we could just use the quadratic formula, right? I don't want to try to factor this guy. I mean, we could, but what's the point? We have the answer, quadratic formula every time, right? So x is negative b plus or minus the square root b squared minus 4ac all over 2a. I'll remember the quadratic formula, right? Yes. Okay, I don't want to do all this arithmetic, so I'm just going to look at the answer. All right, we have very limited time in here. And here's the answer. So there's the critical points. Critical points, 3.7 and 11.5. So 3.7 and 11.5, right? So now we just need to pick out some test points, right? Like we would look at C prime of say 3, see if this is positive or negative. Pick out something in here. We might pick out like the number 4, and then pick out something over here, maybe like 12, and see if these are positive or negative, right? So replace that and then see what you get. And we have limited time. They sum it up for us right here. Here's some test points. So they picked 0 and 10 and 15. I had different numbers. Doesn't matter. You're seeing that over here it's negative, over here it's positive, and over here it's negative. Okay. Plug that into your calculator. So you can see this thing is decreasing, 0, increasing, 0, decreasing. All right. So this guy is minimum, this guy is a maximum, and you can see the intervals for which it's decreasing, increasing, and decreasing, which is what they asked for, right? Which is an important thing to know, right? In business, you want to know when your costs are minimum, when they're maximum, when they're going down, when they're going up, right? There's the graph. What was our function? Our function is just a polynomial here, right? It's an x cubed, right? X cubed was like this, right? If you take x cubed and set it equal to 0 and try to solve it, right? Here's x cubed. You get x equals 0 or 0 or 0. This thing has 3 solutions. They're all 0, right? This is x cubed, but all this other stuff has done stuff to it. All this other stuff is just horizontal shifts or vertical shifts or vertical stretches or horizontal stretches. Those are the 4 things you can do to a function, right? That's what all this other stuff does. Well, if you take x cubed and you stretch it, you end up like that. I mean, x cubed, there should be 3 roots, 1, 2, 3, right? If it's just x cubed by itself, again, it looks like that. The 3 roots are all 0, right? But once you take that thing and you stretch it and amplify it, you can see that the roots kind of spread out, okay? So this guy looks something like that. Well, it's negative, so it's upside down, so it's more like it's a polynomial. And then you move it to the left or to the right or something, okay? And when you take the derivative, you get a quadratic. The quadratic, of course, has these 2 solutions. So, there it is. 3x cubed, right? And I said it looks something like this. There it is. It's been shifted up to the right. Okay. So here are our roots. Boop, boop. Local min and local max. So that's it for 12.1. We need to move. I know we have 7 minutes, but it took us 2 lectures to get through 12.1. We still got to get through 12.2 by Friday, right? So we need to see how far we can get here. We need to get a head start if we can. we got to get through enough of it so I know you can do the homework, right? There we go. The second derivative. Okay, well, if the first derivative is slope, or the rate of change, right? The second derivative is the rate of change of the rate of change, okay? It's acceleration, if you will. So both of these examples, the first derivative is positive, right? Slope is positive, slope is positive, slope is positive. This one, the slope is positive, slope is positive, slope is positive. So everywhere here for both of these, the first derivative is positive, right? Make sense? Okay, but this guy, the slope is positive, but now it's less positive and less positive and less positive. Does that make sense? So the slope is decreasing. So derivatives are about rate of change. The second derivative is talking about the rate of change of the first derivative. Well, the first derivative is decreasing. So for that one, the second derivative would be negative. Now for this guy, the slope is positive, it's even more positive, it's even more positive, it's even more positive, it's even more positive. So the rate of change of the first derivative is positive. So that makes the second derivative positive. So what the second derivative is telling you is it's talking about, geometrically, it's about concavity. It's telling you whether it looks like this or like that. Does that make sense? I'm sorry, the second derivative is about concavity, right? The first derivative just tells you about the slope, whether it's going up or whether it's going down. The second derivative tells you about concavity, whether it's shaped like this or like this. Okay, so let's look at this guy. Right? The slope is positive, less positive, less positive, 0. So it's even less, even less. Everywhere here, the slope is decreasing. Does that make sense? Everywhere, the slope is decreasing. Here, the first derivative is positive. Over here, the first derivative is negative. Right here, the first derivative is 0. But everywhere, the second derivative is positive. I'm sorry, negative. Because the slope is decreasing everywhere. Does that make sense? Each line, the slope is less. The slope is less, the slope is less. The slope goes from positive to negative. It's decreasing the whole time, right? But if you have something like this, all right, here the first derivative is negative, right? Because you are pointing downward. Right here, the first derivative is 0. The slope is 0. Over here, the first derivative is positive, right? But if you look at all the slopes, the slope is increasing everywhere, right? It starts off negative, it gets to 0, and then it becomes positive. The slope is increasing. So everywhere here, the second derivative is positive. All right, does that make sense? All right, it's concavity, okay? So now that you understand what the second derivative means, okay, we're going to have a second derivative test. Sometimes you'll just use the first derivative test. Sometimes you might want to use the second derivative test. You kind of get some of the same information, all right, from both of them. That's telling us anything. It's a boring paragraph. Higher derivatives. So derivatives keep going and going and going. They just tell you rates of change, okay? So like something like a polynomial, if you have a polynomial, once you take enough derivatives, it's just 0, right? Because you get every time you drop a power of x, right? So that's the thing about polynomials. They have a finite number of derivatives, right? Other functions like this guy, right? You can subtract 1 from the exponent subtract 1 from the exponent. You can keep subtracting 1 from the exponent infinitely, right? So you can see something like this actually has an infinite amount of curvature in it, right? Whereas polynomials have a finite amount of curvature. Does that make sense? All right, so in physics, you have position. The change in position with respect to time is velocity, right? The change in velocity with respect to time is your acceleration, right? The change in acceleration with respect to time is called the jerk. It's what gives you whiplash, okay? And then the next 3 derivatives are called the snap, crackle, and pop. They actually are. The ones after that don't have names, okay? So the second derivative, we just use a double prime here, okay? All right, double prime, or this. This is really the derivative with respect to x of the derivative with respect to x of y, okay? You're applying this operator twice, and they write it like this. This is not an x squared, okay? This is dx being applied on the dx, basically, okay? But it looks nice to write it like that, okay? This is not the derivative with respect to x squared. This is the derivative with respect to x operated twice, okay? And we are out of time. So we'll pick up here next time, you know? If you have time, read ahead on this stuff, all right? It helps to read the chapter before class, attempt the homework. All right, let's go.